Yeah, hey, you know what they say about memory management in the C programming language? It's like walking a tightrope, but instead of a safety net, you have a pit of angry alligators waiting to gobble you up if you make a mistake. One of the most notorious challenges when working with C is memory management. Sure, you get control over every single bit of memory like a puppet master, but one misstep and you'll have an angry mob of bugs and crashes at your doorstep. The most common memory issue in C is accessing memory that's already been freed or wasn't allocated in the first place. It's like trying to make a call to someone who's already blocked you, or trying to fit a square peg into a round hole. It just ain't gonna work. Yeah, here's a little code snippet that can cause this kind of problem. In this code, pointer is declared here on line 6, but never initialized, kind of like my love life when I was younger. The program then attempts to shove the number 5 into pointer, which is like trying to fit a squared peg into a round hole. It just won't work. Later, pointer is freed, but the code still tries to write to the number 6 to the memory location where pointer is used to point, like a zombie trying to eat brains, even though it's already dead. Modern compilers though catch that errors. Anyway, if I compile that, you see there is some code running and immediately leads to a segmentation fault. I will now recompile the whole thing here, and you see the compiler in the build log says that here a pointer is not initialized and something going wrong here, build messages, errors. Anyway, the code runs, principally at least, but to avoid memory issues like this, you need always to make sure to initialize pointers before using them and to free memory when you are done with it. You can also use tools like Valgrind or Address Sanitizer to catch some troubles, one of these troublesome bugs before they wreak havoc on your code. To solve the management problem in this code example, you can initialize a pointer before dereferencing it and ensure that the memory is freed after it is no longer needed. So I will now here update this little code that it will work at least. So what we have to do before we can write something to a pointer is we need to initialize it. So in this case, we initialize it with int pointer ptr. That looks suspicious similar here, so we can take that over. And this time we initialize it to malloc. And now we need the size of an int because we want to store an int there, right? Yeah, and that's it already. So if you want to allocate memory and store an int, then you can do it this way. So after that, we need to check if there was really properly space initialized, and malloc gives us for that an option because we can now check if pointer equals null, then something failed, and if not, we just continue. Then in this case return 1, we have an error and we will leave our program main here. So what else we need to do? We want to store some value. We will do that here on line 13 actually. And as you see, now it should work at least. Afterwards, we want also to show that it really worked, and we can do so just by printf. By printf the value of the actual pointer, and that should now be the right value, so 5. And afterwards, of course, we always need to free the pointer before we leave our program here. So now build, run, and as you see, another segmentation fault. But that was only because I did not rebuild the whole project. So if I now build it and run it, the next result here you see is the value of pointer is 5. So at least our program reached line 13, and then we can also be sure that the pointer, the memory, was freed afterwards. Yeah, in this code we allocate memory for a new integer using the malloc function, which returns a pointer to the allocated memory. We check if the allocation was successful by checking if the pointer is null. If the allocation failed, we print an error message and leave the program. Next, we store the value 5 in the allocated memory using the asterisk operator, which dereferences the pointer and allows us to access the memory it points to. We print the value of the pointer using the printf statement to make sure it's storing the correct value. Finally, we freed the allocated memory using the free function, which tells the operating system that we are done with the memory and it can be reused for something else. Yeah, by following these steps, we can avoid memory-related bugs and crashes in our C programs. So there you have it. Memory management in C is like walking through a minefield blindfolded. But with a little bit of care and attention, you can avoid being blown to smithereens and come out of your code intact. Happy coding!